Picture this. You've built this massive, beautifully architected distributed system. It spans the globe. It's handling millions of requests with just millisecond latency. You're feeling great, right? But then, deep down in the architecture, one tiny, seemingly insignificant microservice experiences a localized failure. Maybe a database index takes just a millisecond too long. What happens next? Well, in a poorly architected system, you're about to experience the terrifying reality of the butterfly effect. That single, isolated failure ripples outward. It cascades across the entire network, and suddenly, your glorious global application is completely offline.
Okay, let's look at exactly how that butterfly effect actually plays out. It almost always starts with something we call a retry storm. Imagine that localized failure happens, and a downstream dependency goes offline. Naturally, the clients relying on that dependency try again. They retry the operation. Makes perfect sense, right? But then, the clients of those clients also experience a delay, so they retry. What you get is this exponential, compounding growth in traffic. The system becomes utterly overloaded because it's now trying to process regular organic traffic on top of a massive wave of automated retry traffic, all while its underlying performance is already degraded. It is, quite literally, a self-inflicted denial of service attack.
Welcome to The Explainer. Today, we're putting on our system architect hats and tearing down the blueprint of hyperscale resilience. We're diving into load shedding and how big tech prevents total system collapse. If you're building modern infrastructure, the very first mindset shift you absolutely need to make is this. Functioning despite failures isn't an edge case, it is the normal mode of operation. Failure is inevitable. It is going to happen. So today, we're going to see exactly how the best engineering teams design for it.
Here's our architectural blueprint for today. We'll start with the butterfly effect failure, dissect the anatomy of load shedding, explore prioritization and graceful degradation, look at taming tail latency, and finish up with some real-world architecture examples. All right, part 1, the butterfly effect failure and hyperscale fragility.
So why exactly are these hyperscale environments so profoundly vulnerable to minor hiccups? Well, it all comes down to scale. Just look at this number, 30,000. In a modern environment, like Uber, for example, a single ride-hailing request from your phone doesn't just hit one server and return a result. That single request traverses around 500 discrete microservices, and in doing so, it fires off over 30,000 remote procedure calls, or RPCs. This wild combinatorial explosion of interconnections means there are literally tens of thousands of potential failure modes on every single swipe of the app. At this scale, even a tiny degradation in a completely non-critical service can cascade backward and take down your entire core business. Moving on to part 2, anatomy of load shedding, the architectural antidote. If a retry storm threatens to exhaust all our resources and take down those 500 microservices, what's our defense? It's load shedding. Now, I know it sounds completely counterintuitive. As engineers, we want to serve every single user request. We hate dropping anything. But load shedding is the intentional act of dropping or rejecting traffic to protect the broader system. Think of it like triage in a hospital emergency room. When resources are completely tapped out, the doctors are swamped, and the waiting room's overflowing, you just can't treat everyone at once. You have to prioritize the most critical, life-threatening cases first, and unfortunately make the others wait or turn them away. Because if you don't do that, the entire hospital collapses, and literally no one gets saved. In software, when back pressure builds, you must shed the load to survive. Part 3, prioritization and graceful degradation. Let's talk about surviving that storm. So, how does a system mathematically and structurally decide who gets the hospital bed and who gets sent home? This brings us to graceful degradation. A well-architected system has to maintain its core critical functionality even when facing massive resource exhaustion. A fundamental architectural principle here is this: non-critical service failures must never cascade to impact core business functionality. Think about it. If the specific microservice that displays a user's promotional discount goes down, that user shouldn't be blocked from actually booking the ride or checking out their shopping cart, right? The UI should gracefully degrade, maybe hiding the broken discount feature entirely, while the primary transaction just keeps flowing unhindered. And this perfectly highlights the trade-offs we have to make, which are often dictated by the CAP theorem. When a network partition hits or the system is under extreme stress, you have to choose between consistency on one hand and availability on the other. Financial transactions, they demand consistency. Every node must agree on your bank balance, even if it means rejecting requests. But e-commerce systems, they usually prioritize availability. If a retail platform is getting crushed during a peak holiday rush,
It's actually perfectly acceptable to show a user slightly out-of-date inventory data. Maybe it says 5 items are left instead of 4. That's fine, as long as it keeps that shopping cart highly responsive and the checkout flowing. That is intentional, graceful degradation.
All right, part 4. Taming tail latency. Time to start obsessing over the P99.
Once you've stopped the system from fully collapsing, you still have to deal with the silent killer of user experience, latency. Let's be real. If you're celebrating a great average latency, your P50, you are looking at a vanity metric. True reliability engineering demands obsessing over the P99 tail. P50 just means half your requests are faster, half are slower. But if you have an endpoint with an average latency of 50 milliseconds, you might still have 1% of your users waiting 2 full seconds because of hidden bottlenecks. And remember those 30,000 RPCs we talked about? When you fan out traffic like that, nearly 1 in 10 user requests will hit that 1% edge case. The P99 is the true measure of your system's health under load.
Google engineers Jeff Dean and Luis-Andre Barroso hit the nail on the head here. In large systems, rare slow events are no longer rare. Because a single user action touches so many different nodes, if just one node has a 1% chance of being slow, well, the mathematical probability that the user's overall request will be slow quickly approaches 100%. At hyperscale, edge cases aren't anomalies. They are constant, everyday operational realities.
Take a look at this benchmark data. Everything looks incredibly smooth initially, right? The P90 is totally fine. But look way out at the far right, out at the P99 and P99.9 percentiles. You see these massive, jagged spikes where the response time just shoots up, completely breaking the SLA requirements. What causes those? Usually it's transient issues. Things like a garbage collection pause in a JVM, a noisy neighbor on shared cloud hardware, or a temporary network blip. For 99% of people, the system is lightning fast, but for that 1%, it feels entirely broken. So how do we actually fix it? Well, we listen to performance engineers like Brendan Gregg. He points out that if you only look at your CPU charts, you're completely blind to where the time is actually going. You've got to look off CPU. You have to realize that your threads are often just waiting. They spend enormous amounts of time waiting on locks, waiting on disk I/O, or waiting on downstream microservices to respond. Finding and eliminating that hidden waiting time, that is how you destroy user-facing latency. Here is your pragmatic playbook for engineering a predictable request path. Step 1. Instrument end-to-end budgets. Put strict deadlines on your requests so timeouts don't cascade. Step 2. Find your P99 contributors using distributed tracing. Step 3. Remove avoidable network hops. Co-locate those hot dependencies. Step 4. Add tail controls like jittered retries to smooth out traffic spikes. And Step 5. Isolate and load shed before you scale. Bound your queues, apply back pressure, and fail fast. Now, here's a highly advanced tactic to cut that P99 tail. Hedged requests. If you really want to cut the tail, try racing your replicas. If a request hits a 95th percentile timeout, meaning it's taking unusually long, you immediately fire off a duplicate secondary request to a different server replica. Then, you just serve whichever response comes back first. It drastically cuts latency variance. But be super careful here. You must strictly cap how many hedges you allow. Otherwise, congratulations, you've just triggered your own retry storm. Finally, part 5. Real-world architecture examples, where we test the absolute limits. So, how do these theoretical concepts get physically implemented and stress-tested in the real world? It's all about chaos engineering. Organizations utilizing AWS, or pioneers like Netflix with their famous Chaos Monkey, they prescribe injecting severe failures directly into production. They generate artificial traffic surges, they max out CPU and memory to test resource exhaustion, they deliberately take down downstream dependencies, and they initiate primary cascading failures. If you don't test your disaster recovery protocols in peacetime, I promise you they will absolutely fail you during a real war. And when we're looking at high-performance architecture, we have to talk about the LMAX disruptor. This is used in lightning-fast financial trading. They realize that traditional queues create terrible latency bottlenecks because of write contention between threads. So they applied something called mechanical sympathy. Essentially, they designed software that plays nicely with how the physical CPU cache actually works. They replaced queues entirely with lock-free ring buffers using a single writer, multiple reader coordination model. This completely eliminates thread contention. It allows for incredibly smooth back pressure and flow control, meaning the application itself becomes aware of consumption rates and perfectly sheds load without ever stalling out. But look, despite the best architecture in the world, outages happen. And when you're in the war room operating a massive distributed system under collapse, you have to follow the golden rule of outages. Mitigation now, investigation tomorrow. When the alarms are blazing, it is so incredibly tempting to try and debug the code, find the root cause, and push a quick forward fix. Don't do it. Just don't. A rushed fix in the middle of a panic is the absolute best way to cause a second, much worse outage. Your only job in that moment is to shed the load, roll back the deployment, and stabilize the patient. The deep dive, well, that can wait until Monday morning.
Which leaves us with this final, provocative thought. Take a look at your own architecture right now. Are you still optimizing your systems purely for the happy path? You know, assuming the network is perfectly reliable, latency is zero, and resources are infinite? Or are you architecting for the inevitable failure? Because out in the wild, the retry storms are always brewing. Thanks for joining me on this explainer. Keep building resilient systems, and I'll catch you next time.